Tonight, we are going to talk about the most underappreciated force in the universe. Not the most powerful, not the most familiar, the most underappreciated. The one that almost nobody thinks about when they think about the forces of nature. The one that gets overshadowed by gravity bending space-time and electromagnetism producing light and the strong force confining quarks. The one that operates so quietly, at such a short range, so briefly, that for decades physicists were not even sure it really existed as a separate force, and not just a strange variation of something already known. It is called the weak nuclear force. And here is what almost nobody tells you about it. The weak force is the reason the sun shines. Not gravity, not the strong force alone. The weak force. Without it, the fusion reactions in the solar core would stop. The sun would go dark. Not slowly, not gradually, but fundamentally. The specific chain of reactions that converts hydrogen into helium and releases the energy that has warmed the Earth for 4.5 billion years requires the weak force to take the first and most essential step. Without the weak force doing something no other force in nature can do, the sun could not burn. The weak force is also the reason the neutron in your atoms is stable. A free neutron, a neutron outside the safety of a nucleus, dies in about 10 minutes. The weak force kills it. It transforms the neutron into a proton, an electron, and an antineutrino. Without the weak force doing this transformation, nuclear physics would look completely different. The elements as we know them would not exist. And the weak force is the only force in the universe that treats left and right differently. Every other force, gravity, electromagnetism, the strong force, is perfectly symmetric between left and right. Mirror a physical process governed by these forces, and you get a process that also obeys their rules. But mirror a process governed by the weak force, and you get something that is subtly, unmistakably, but profoundly wrong. Something the universe does not allow. The universe, at its most fundamental level, has a handedness, a preference, and the weak force is what reveals it. By the end of tonight, you are going to understand what the weak force actually is, why it can do something no other force can, what mirror symmetry breaking means, and why its discovery was described as the biggest shock in physics since the theory of relativity, and why the weak force's tiny asymmetry between matter and antimatter may be the reason the universe contains anything at all. Let us begin. Let us start with something you probably learned in school and then forgot about immediately. Radioactive decay. Elements that are unstable, that spontaneously emit radiation and transform into different elements over time. Uranium decaying into lead. Carbon-14 decaying and allowing archaeologists to date ancient materials. Iodine-131 decaying in the thyroid. You might have learned about half-lives, the time it takes for half a radioactive sample to decay. But you probably never learned what actually happens at the particle level when an atom decays. For most of the history of physics, neither did physicists. Radioactivity was discovered by Henri Becquerel in 1896, when he found that uranium salts emitted some kind of radiation that could fog photographic plates even in the dark. Marie Curie and Pierre Curie characterized the phenomenon further, identifying different types of radiation and finding new radioactive elements. By the early 20th century, physicists knew that radioactivity existed and had characterized its effects. But the mechanism, what was actually happening inside the nucleus when it decayed, was completely unknown. There were three types of radiation discovered early on. Alpha radiation, which turned out to be helium nuclei emitted from heavy atomic nuclei. Beta radiation, which turned out to be electrons emitted from nuclei. And gamma radiation, which turned out to be high-energy photons. Each type came from different nuclear processes. And the beta decay, the emission of electrons from nuclei, would turn out to harbor one of the deepest mysteries in physics. The mystery was this. When a nucleus undergoes beta decay and emits an electron, the electron does not always come out with the same energy. In alpha decay, the emitted alpha particle always has a specific, definite energy characteristic of the decay. In gamma decay, the photon always has a specific energy. But the electrons from beta decay come out with a range of energies, from 0 up to some maximum. Any energy in that range is possible. This was deeply disturbing. The law of conservation of energy says that energy cannot be created or destroyed. In a nuclear decay, you start with a nucleus of definite mass, and end with a different nucleus of definite mass. The difference in mass, converted by Einstein's equation to energy, should equal the energy of whatever is emitted. If the only thing emitted is an electron, the electron should always have exactly that energy. But it did not. It had variable energy. Where was the missing energy going? Some physicists, including Niels Bohr, seriously considered the possibility that energy conservation simply did not hold in nuclear beta decay, that energy could disappear at the quantum level, that one of the most fundamental laws of physics was violated in the nucleus. Wolfgang Pauli refused to accept this. In 1930, he wrote a famous letter to colleagues attending a physics conference, a letter he cheekily addressed to the dear radioactive ladies and gentlemen, in which he proposed a daring solution. The missing energy was not missing. It was being carried away by a particle that nobody had yet detected. A particle so ghostly, so reluctant to interact with anything, that it passed through all existing detectors completely unobserved. A particle with no charge, very little or no mass, that accompanied the electron in beta decay but escaped without being seen. Pauli called this hypothetical particle the neutron. Later, when the actual neutron was discovered in 1932 by James Chadwick, Enrico Fermi renamed Pauli's proposed particle the neutrino, the little neutral one. And the neutrino became one of the most ghostly and most important predictions in the history of physics. It was not actually detected until 1956, 26 years after Pauli proposed it. Clyde Cowan and Frederick Reynes used the intense flux of antineutrinos from a nuclear reactor to catch a handful of interactions in a large detector, enough to confirm that the neutrino was real. Pauli, who had once said he had committed the cardinal sin of theoretical physics by predicting a particle that could never be detected, received a telegram telling him of the confirmation. He was reportedly overjoyed. But the neutrino was just the beginning of understanding what beta decay actually was. The deeper question was not what was emitted. It was what force caused the emission. What was the mechanism behind the transformation of a neutron into a proton? Because that is what beta decay is. At the fundamental level, beneath the nucleus, beneath the proton and neutron, a down quark inside the neutron transforms into an up quark. One type of fundamental particle becomes a different type of fundamental particle. Not a collision, not a binding or unbinding. An actual transformation of identity. A quark changes what it is. And this is the most remarkable thing the weak force does. The thing that sets it apart from every other force in nature. Every other force acts between particles without changing what they are. Gravity pulls masses together without changing the masses. Electromagnetism pushes or pulls charges without changing the charges. The strong force confines quarks without changing their quark type. But the weak force converts particles from one type to another. It is the only force in the universe with this power. The only force that can look at a down quark and turn it into an up quark. The only force that can change the fundamental identity of a particle. This is not a minor technical capability. It is the capability that makes nuclear physics possible. Without it, there would be only one type of quark. There would be no neutrons. There would be no nuclear reactions. There would be no stellar nucleosynthesis. There would be no elements heavier than hydrogen. There would be no chemistry. There would be no you. The weak force is the engine of particle transformation, the mechanism by which the universe shuffles its fundamental cards. Now let us understand how it does this. What is the mechanism? What carries the weak force the way photons carry electromagnetism and gluons carry the strong force? The carrier particles of the weak force are called the W and Z bosons. There are three of them: the W plus boson, the W minus boson, and the Z boson. They are massive, extremely massive compared to other force carriers. The W bosons each have a mass of about 80 gigaelectronvolts, roughly 85 times the mass of a proton. The Z boson has a mass of about 91 gigaelectronvolts, about 97 times the mass of a proton. This enormous mass is the key to understanding everything unusual about the weak force. A massive force carrier means a short-range force. This is the Yukawa relation, first derived by Hideki Yukawa in the context of the nuclear force. The range of a force is inversely proportional to the mass of its carrier. The photon is massless, so electromagnetism has infinite range. Gravity, also carried by a massless particle in the quantum theory, also has infinite range. The W and Z bosons are enormously heavy. So the weak force has an extremely short range. How short? About 1,000th of the diameter of a proton. That is the range within which the weak force operates. Step outside that range, and the force drops to essentially nothing. This is why you have never felt the weak force. This is why it took so long to discover. This is why it seems weak. Not because the fundamental coupling of the force is particularly small. In fact, the coupling of the weak force is comparable to that of electromagnetism. It seems weak because its range is so incredibly short that at any distance where you can actually observe it, the force has already dropped off to almost nothing. The W bosons are particularly interesting because they carry electric charge. The W plus has positive charge and the W minus has negative charge. This is unusual for a force carrier. The photon, carrier of the electromagnetic force, has no electric charge. The gluons of the strong force carry color charge, but not electric charge. The Z boson is electrically neutral, but the W bosons carry electric charge, and this is what allows them to change the electric charge of particles they interact with. When a down quark emits a W minus boson, the quark changes from having charge minus 1/3 to having charge plus 2/3. It has become an up quark. The W minus boson carries away the charge difference. It then decays into an electron and an antineutrino. The net result: a down quark has become an up quark, and an electron and antineutrino have been produced. This is beta decay. This is what happens when a neutron decays. One of its down quarks emits a virtual W-, becomes an up quark, turning the neutron into a proton. The W- immediately decays into an electron and an antineutrino. Everything is accounted for. Energy is conserved. Charge is conserved. The neutrino carries away the variable share of energy that had puzzled physicists for decades. The W boson is the key, the mechanism of transformation, the particle that makes it possible for one quark type to become another, for a neutron to become a proton, for hydrogen to become helium in the core of the sun, for the elements to be built up from simpler ingredients. But the W and Z bosons were not predicted until the 1960s and not confirmed experimentally until 1983. For decades, the weak force was described by a theory that worked but was known to be incomplete. Fermi had developed a theory of beta decay in 1933 that correctly described the process mathematically but did not include carrier particles. It treated the weak interaction as a point contact, happening at a single point in spacetime with no mediating particle. Fermi's theory worked at low energies, but was known to break down at high energies, producing predictions of infinite probabilities, which is physics telling you that the theory is wrong or incomplete. The completion of the theory required the Higgs mechanism, which we have already explored in depth. Without the Higgs mechanism giving mass to the W and Z bosons, the electroweak theory was mathematically inconsistent. The Higgs mechanism resolved the inconsistency. And once the electroweak theory was complete and mathematically consistent, the W and Z bosons were predicted with specific masses. The prediction was precise. The masses were calculated. The only question was whether experiments could reach the energy needed to create particles that heavy. Carlo Rubbia, a brilliant and forceful Italian physicist, convinced CERN to build a proton-antiproton collider powerful enough to produce W and Z bosons. The superproton synchrotron was converted to collide protons with antiprotons at center of mass energies around 540 gigaelectronvolts. Two enormous detectors, UA1 and UA2, were built to look for the signatures of W and Z boson production and decay. The W boson was announced in January 1983. The Z boson was announced months later. The masses matched the theoretical predictions with remarkable precision. It was one of the greatest confirmations of a theoretical prediction in the history of physics. Carlo Rubbia and Simon van der Meer, who had developed the key technology of stochastic cooling that made the antiproton beam possible, received the Nobel Prize in Physics in 1984, one of the fastest Nobel Awards in history. The committee could not wait. Now let us talk about something even stranger. Something that shocked physics in 1956 the way almost nothing has shocked physics before or since. The discovery that the weak force violates mirror symmetry. Mirror symmetry, also called parity, is the idea that the laws of physics look the same in a mirror. If you film a physical process and then mirror the film, flipping left and right, The mirrored version should still show a process that obeys the laws of physics. For most physical processes, this is obviously true. A ball bouncing, a wave moving, two billiard balls colliding. Mirror any of these and you get something that looks perfectly physical. Nothing in the mirror version is wrong or impossible. Before 1956, most physicists assumed this was true of all physical processes. That parity was a fundamental symmetry of nature. That the laws of physics were completely symmetric between left and right. This seemed obvious. Why would nature prefer one-handedness over another? What would even determine which direction was left and which was right if the laws treated both the same? In 1956, two theoretical physicists, Tsung-Dao Lee and Chen-Ning Yang, reviewed the experimental evidence for parity conservation in the weak interaction and found something disturbing. The evidence that parity was conserved in the strong force in electromagnetism was solid and extensive. The evidence that parity was conserved in the weak force was essentially non-existent. Nobody had actually tested it carefully in weak interactions. They had assumed it was conserved without checking. Lee and Yang proposed that parity might be violated in weak interactions and suggested specific experiments that could test this. Their proposal was met with considerable skepticism. Most physicists were reluctant to believe that nature would be so asymmetric. But the experiments were done. Chien-Shiung Wu, a Chinese-American physicist at Columbia University, designed and carried out an extraordinarily difficult experiment. She cooled cobalt-60 nuclei to extremely low temperatures, near absolute zero, and aligned their nuclear spins in a magnetic field. Aligned spins mean the nuclei are all rotating in the same direction, giving the system a definite handedness. She then measured the direction in which the electrons from beta decay were emitted relative to the spin axis. If parity were conserved, the electrons should be emitted equally in both directions along the spin axis, forward and backward. The process and its mirror image should be identical. They were not. The electrons were emitted preferentially in one direction. Not randomly, not equally. One direction was favored. The weak force was treating left and right differently. The universe, at its most fundamental level, was not symmetric between its own mirror image. The result was announced in early 1957. The reaction among physicists was immediate and profound. Wolfgang Pauli, upon hearing the result, said he could not believe that God is a weak left-hander, expressing his disbelief that nature would show such asymmetry. Richard Feynman allegedly made a bet against parity violation and lost. Leon Lederman described the discovery as the most shocking event in physics since the theory of relativity. Lee and Yang received the Nobel Prize in Physics in 1957, the year after their theoretical proposal. Wu, who had done the actual experimental work that confirmed it, did not share the Nobel Prize, an exclusion that has been widely criticized as one of the more notable oversights in the history of the Nobel Committee. But what does parity violation actually mean? What is the physical content of this discovery? It means that the universe has a preferred handedness, a preference for left over right, or more precisely, a preference for a specific combination of handedness and direction. The weak force, in its interactions, does not treat left-handed particles and right-handed particles the same. It couples only to left-handed particles and right-handed antiparticles. The W bosons, when they are emitted or absorbed, interact exclusively with the left-handed component of particles. What does left-handed and right-handed mean for a particle? It refers to the relationship between the particle's spin and its direction of motion. A left-handed particle is one where the spin axis points opposite to the direction of motion, like a left-handed screw. A right-handed particle has its spin axis pointing in the direction of motion, like a right-handed screw. For massless particles, this handedness, called helicity, is a fixed property of the particle. A massless left-handed particle is always left-handed, regardless of who is observing it. The neutrino, the ghostly particle that accompanies beta decay, is always left-handed. Every neutrino ever produced in any weak interaction anywhere in the universe is left-handed. There are no right-handed neutrinos. Or if there are, the weak force does not interact with them, making them completely invisible to any detector we have. The antineutrino is always right-handed. The universe makes only left-handed neutrinos and only right-handed antineutrinos, because the weak force, which is the only force that produces them, only knows how to make one type. This is deeply asymmetric, and it is not an accident. It is a fundamental property of the weak force as described in the Standard Model. The weak force is intrinsically chiral. It has a handedness built into its most fundamental structure. The W and Z bosons couple to the left-handed components of quarks and leptons and to the right-handed components of antiquarks and antileptons. This is not a consequence of some deeper principle. It is a brute fact about the structure of the Standard Model, a fact that we do not currently have a deeper explanation for. The question of why the weak force is left-handed, why it prefers left-handed particles to right-handed ones, is one of the unanswered questions in fundamental physics. It may have something to do with the way the symmetry of the electroweak force was broken. It may be connected to the origin of the matter-antimatter asymmetry. Or there may be a deeper theory beyond the Standard Model in which left-right symmetry is restored at higher energies, and the apparent left-handedness of the weak force at low energies is a consequence of symmetry breaking. Physicists have proposed such theories, called left-right symmetric models. Whether they are correct is an open experimental question. Now let us talk about the deepest consequence of the weak force, the one that connects it to the most fundamental question in all of physics. Why is there anything? When the universe began in the Big Bang, the laws of physics produced matter and antimatter in equal quantities. Every particle that was created was accompanied by an antiparticle, protons and antiprotons, electrons and positrons, quarks and antiquarks. The universe began in perfect balance between matter and antimatter. But a universe in perfect balance between matter and antimatter would not last long. Matter and antimatter annihilate each other on contact, converting back into pure energy. In a perfectly balanced universe, all the matter and all the antimatter would find each other and annihilate. The universe would be left with pure radiation and nothing else. No particles, no atoms, no stars, no people. And yet here we are. The universe contains matter, enormously more matter than antimatter. The observable universe has essentially no natural antimatter in it. Whenever antiparticles are produced in cosmic ray collisions or particle accelerators, they quickly find matter particles and annihilate. The universe we live in is overwhelmingly made of matter. This asymmetry between matter and antimatter, this survival of matter over antimatter, is called the baryon asymmetry of the universe, and it is one of the deepest unsolved problems in physics. For a universe to end up with more matter than antimatter, starting from a balanced beginning, three conditions must be met. These were identified in 1967 by Andrei Sakharov, the Soviet physicist who would later become famous as a dissident and human rights activist. Sakharov's conditions state that the early universe must have undergone processes that violate baryon number conservation, that violated the symmetry between matter and antimatter called CP symmetry, and that occurred out of thermal equilibrium. The second condition, CP violation, is directly connected to the weak force. CP symmetry is a combination of two symmetries: C symmetry, which swaps particles for antiparticles, and P symmetry, parity, which mirrors left and right. Although the weak force violates P symmetry alone, it was long thought that the combined CP symmetry might still be preserved. That while left and right were treated differently, the combination of swapping particles for antiparticles and mirroring left and right might still be a symmetry of the weak force. This was found to be wrong in 1964. James Cronin and Val Fitch, studying the decay of neutral kaons, particles made of quarks and antiquarks, found that the combined CP symmetry was violated. The decay rates of certain kaon processes were slightly different from the CP mirrored versions of those same processes, by a tiny amount, a few parts in 1,000, but definitely violated. CP violation was confirmed, and Cronin and Fitch received the Nobel Prize in 1980. The CP violation in kaon decays, and subsequently found in B meson decays and other systems, is a property of the weak interaction. It arises from a complex phase in the matrix of numbers that describes how the weak force mixes between the different generations of quarks. This matrix, called the CKM matrix after Kabibo, Kobayashi, and Moskawa, who developed its theoretical description, contains a complex phase that cannot be removed and that causes CP violation. The three physicists who developed this theory received the Nobel Prize in 2008. But here is the deep problem. The amount of CP violation in the Standard Model, the amount generated by the complex phase in the CKM matrix, is far too small to account for the observed matter-antimatter asymmetry of the universe. By many orders of magnitude, the CP violation that we have measured in particle physics experiments is real but insufficient to explain why we exist. This means one of two things. Either our understanding of how the baryon asymmetry was generated is wrong, or there are additional sources of CP violation beyond those in the Standard Model. The second option is more attractive to most physicists. It suggests there is physics beyond the Standard Model that contains more CP violation than the Standard Model does. Finding that additional CP violation, identifying its source, is one of the major goals of current and future particle physics experiments. Neutrinos are a particularly promising place to look. The neutrino sector of the Standard Model has its own mixing matrix, analogous to the CKM matrix for quarks, called the PMNS matrix. And the PMNS matrix may contain its own complex phase, its own source of CP violation. Measuring weather neutrino oscillations, the quantum mechanical process by which neutrinos transform from one type to another as they travel, behave differently from antineutrino oscillations, would be evidence of CP violation in the neutrino sector. Several large neutrino experiments around the world, including experiments at Fermilab in Illinois and at the Super Kamiokande detector in Japan, are looking for exactly this. Early results from the T2K experiment in Japan have shown hints of CP violation in neutrino oscillations, hints that are consistent with a large CP violating phase in the PMNS matrix. These are not yet definitive. They are hints, at about 2 to 3 sigma significance, well below the 5 sigma standard for a discovery. But they are suggestive. They suggest that the neutrino sector may contain significantly more CP violation than the quark sector. If confirmed, this would be enormously significant. It would point toward a mechanism called leptogenesis, in which CP violating processes in the neutrino sector in the early universe generated a lepton asymmetry, in excess of leptons over antileptons, which was then converted into a baryon asymmetry by other processes. It would connect the existence of matter in the universe to the specific, measurable properties of neutrino oscillations. It would mean that the reason you exist, the reason the universe contains matter rather than nothing, is encoded in the way neutrinos change flavor as they travel through space. In a quantum mechanical property of the ghostliest, most elusive particles in the universe. And the mechanism behind that flavor changing, behind neutrino oscillations, behind the CP violation that may explain everything, is the weak force. The force that no one thinks about. The force that seems peripheral and obscure. The force that operates only within a thousandth of a proton diameter. That force may be the reason the universe has something in it rather than nothing. Let us also spend time understanding the connection between the weak force and the sun, because this is where the weak force's unique capability, its ability to transform one particle type into another, has its most dramatic consequences for life on Earth. The fusion reactions in the sun begin with protons. The sun's core is a hot, dense plasma of hydrogen nuclei, which are just protons. For the sun to shine, those protons must be converted into helium nuclei. A helium, for nucleus, contains 2 protons and 2 neutrons. So somewhere in the chain of reactions, protons must be converted into neutrons. But nothing in the sun can do this except the weak force. Gravity cannot change a proton into a neutron. The electromagnetic force cannot. The strong force cannot. Only the weak force, with its unique ability to transform quark types, can take a proton and turn it into a neutron. The first step in the proton-proton chain, the sequence of fusion reactions that powers the sun, is the fusion of 2 protons to form a deuterium nucleus. A deuterium nucleus contains 1 proton and 1 neutron. So 2 protons come together, and one of them must transform into a neutron. This transformation requires a weak force interaction. One of the protons emits a virtual W+ boson, converting one of its up quarks into a down quark, turning the proton into a neutron. The W+ immediately decays into a positron and a neutrino. This reaction, P plus P gives D plus positron plus neutrino, is the rate-limiting step of the proton-proton chain. It is the bottleneck, and it is so slow, so improbable for any given pair of protons, precisely because it requires the weak force. The probability of two protons in the solar core undergoing this reaction in any given collision is incredibly small. On average, any given proton in the Sun will wait about 10 billion years before successfully fusing with another proton via this reaction. 10 billion years is approximately the current age of the universe. This extreme rarity is why the Sun has been burning for 4.5 billion years and will continue for another 5 billion. If the reaction were faster, if the weak force were stronger, or if some other force could do this job, the Sun would have burned through its hydrogen fuel long ago and gone dark. The weakness of the weak force, the fact that this reaction is so improbable, is what gives the Sun its stability and its longevity. The weakness of the weak force is what gave life on Earth 4.5 billion years to evolve. The weakness of the weak force is why you had enough time to exist. This is perhaps the most intimate connection between a force of nature and the existence of life. Not an abstract connection through chemistry or through the existence of elements. A direct, essential connection. The Sun burns because the weak force transforms protons into neutrons. The Sun burns slowly and steadily because the weak force makes this transformation rare. Life had time to evolve because the Sun burned slowly and steadily. You exist because the weak force is weak. Now let us think about the neutrino more carefully, because the neutrino is in many ways the emblem of the weak force. The particle that the weak force produces most readily and that nothing else in nature interacts with. Right now, approximately 100 trillion neutrinos are passing through your body every second. Not occasionally, every second. 100 trillion. Most of them come from the Sun, produced in the very proton-proton fusion reactions we just discussed. A small fraction come from other stars, from cosmic ray interactions in the atmosphere, from the radioactive decay of elements inside the Earth, from nuclear reactors if you are near one. And essentially none of them interact with you. In your entire lifetime, the expected number of solar neutrinos that will interact with any atom in your body is roughly 0. You will live and die, and 100 trillion neutrinos will pass through you every single second, and not one of them will leave any trace. This is because the weak force, the only force that neutrinos respond to, has an effective cross-section, an effective interaction area, that is incredibly small. A neutrino can pass through a light year of solid lead with only a 50% chance of interacting. 1 light year of solid lead, and the neutrino has even odds of passing through without incident. To detect neutrinos at all requires enormous detectors and enormous neutrino fluxes. The Super Kamiokande detector in Japan is a tank of 50,000 tons of ultra-pure water buried 1 kilometer underground to shield it from cosmic ray background. With that much water and the intense flux of neutrinos from the Sun, roughly 15 solar neutrino interactions are detected per day. 15 per day, from a flux of 100 trillion per square centimeter per second. That is the weakness of the weak force made concrete and numerical. And yet these ghostly non-interacting particles carry information that nothing else can carry. Because they pass through the Sun's core, through all the layers of plasma and radiation that light takes 100,000 years to diffuse through, neutrinos escape from the solar core in about 2 seconds, carrying direct information about the nuclear reactions happening at the very center. They carry information from the interior of stars, from supernova explosions, from places that are completely opaque to light. Neutrino astronomy is a window into the universe that electromagnetic astronomy cannot provide. The detection of neutrinos from supernova 1987A, a supernova in the Large Magellanic Cloud that was observed in February 1987, was a landmark in this regard. 24 neutrinos were detected in the span of about 12 seconds in neutrino detectors in Japan and the United States. 24 neutrinos, from the collapse of a stellar core 168,000 light-years away. 24 neutrinos arriving hours before the light from the explosion, because the neutrinos escaped immediately while the light took hours to make its way through the expanding envelope of gas and debris. Those 24 neutrinos confirmed the theoretical picture of how supernovae work, confirmed that the energy released in a stellar core collapse is carried primarily by neutrinos, and confirmed that neutrinos have masses small enough that they travel very close to the speed of light across intergalactic distances. And neutrinos having mass is itself something the original Standard Model did not predict. The original formulation of the Standard Model assumed neutrinos were massless. The discovery of neutrino oscillations, the transformation of one type of neutrino into another as they travel, proved that neutrinos must have mass. Zero-mass neutrinos cannot oscillate between types. The oscillation is only possible if neutrinos have mass, small mass, but non-zero mass. This was itself a major discovery, confirmed in 1998 by the Super Kamiokande experiment using atmospheric neutrinos produced by cosmic ray interactions. Takaaki Kajita, who led that analysis, and Arthur MacDonald, who led a complementary discovery at the Sudbury Neutrino Observatory in Canada, shared the Nobel Prize in Physics in 2015 for the discovery of neutrino oscillations and therefore neutrino mass. Neutrino mass is physics beyond the Standard Model. The original Standard Model predicted zero neutrino mass. The real neutrinos have non-zero mass. Something must be added to the Standard Model to accommodate this fact. What that something is remains an open question. The most popular theoretical framework involves particles called right-handed neutrinos, very heavy particles that have never been observed, which through a mechanism called the seesaw mechanism give the observed light neutrino masses. The heavy right-handed neutrinos, if they exist, would also naturally produce the CP violation in the neutrino sector that could explain the matter-antimatter asymmetry of the universe. The weak force, through the neutrino, connects to some of the most important open questions in all of physics. The origin of neutrino mass. The source of CP violation sufficient to explain the matter-antimatter asymmetry. The nature of the right-handed neutrino. Whether the neutrino is its own antiparticle, a Majorana fermion, or distinct from its antiparticle, a Dirac fermion. Each of these questions is being actively investigated by experiments around the world. The weak force, the most overlooked force, the force that seems peripheral and obscure, sits at the center of some of the deepest mysteries about the origin of the universe and the reason matter exists. Tonight you have followed it from the decay of the neutron to the burning of the sun to the violation of mirror symmetry to the possible explanation for why the universe contains anything at all. You have followed it from Pauli's desperate letter proposing the neutrino to Wu's experiment with cold cobalt nuclei, shattering the assumption of mirror symmetry, to Cronin and Fitch finding CP violation in kaon decays, to the confirmation of the W and Z bosons, to the discovery of neutrino oscillations. You have followed the history of a force that was theorized before it was understood, that violated assumptions that seemed unshakable, that turned out to be unified with electromagnetism at high energies, and that may hold the key to why the universe is not empty. The weak force is weak at the distances and energies of everyday life. But at the fundamental level, it is anything but marginal. It is the only force that can transform particles from one type to another. It is the only force that breaks mirror symmetry. It is the source of the CP violation that may explain everything. It is the force that powers the sun and makes the elements and produces the neutrinos and drives the nuclear reactions on which all of stellar physics depends. Right now, inside the core of the sun, a proton is about to emit a virtual W boson. The W boson will decay in a fraction of a trillionth of a second. The proton will become a neutron. A positron and a neutrino will be born. The neutrino will travel outward at nearly the speed of light, passing through the entire sun in 2 seconds, crossing the 150 million kilometers to Earth in 8 minutes, passing through the entire Earth without noticing it, and continuing into the cosmos. And the energy released in that transformation, that tiny weak force interaction in the solar core, will eventually make its way to the surface of the sun as light, as the sunlight that warms the Earth. That makes photosynthesis possible. That drives the weather and the water cycle and the wind. That ultimately powers every living thing on the surface of this planet. The sun shines because of the weak force. You exist because of the weak force. The universe contains matter rather than nothing, possibly because of the weak force. And almost nobody thinks about it. Tonight, you do. And that changes how the world looks. Not the world you see with your eyes, but the world underneath. The world of forces and transformations and symmetry breaking and the billion-year consequences of a quantum interaction that lasts less than a trillionth of a second. That world is always there, running underneath everything. The weak force doing its quiet, essential, boundary-breaking work. In the sun, in every radioactive nucleus, in every neutrino passing through your body right now. The most overlooked force in the universe, doing the most essential work. Without pause, without recognition, without ever stopping. Let us spend more time on something that deserves deeper attention. The electroweak unification. Because understanding what it means for the weak force in electromagnetism to be the same force at high energies is one of the most profound ideas in all of physics, and it reveals something deep about how the universe works that most people never encounter. At the energies of everyday life, electromagnetism and the weak force look completely different. Electromagnetism is long-range. It holds electrons and atoms. It carries light across the universe. Its carrier, the photon, is massless. The weak force is incredibly short-range. It operates only inside the nucleus. Its carriers, the W and Z bosons, are enormously heavy. The two forces could not appear more different. And yet they are the same force. Or more precisely, they are two different manifestations of the same underlying force, an electroweak force that was unified in the early universe and that remains unified in the mathematics of the Standard Model. To understand this, you need to understand what it means for forces to be unified. It does not mean they are identical. It means they are described by the same underlying mathematical structure, and their apparent differences arise from the way symmetry was broken when the universe cooled. The electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s, describes both forces as manifestations of a single-gauge symmetry, a mathematical symmetry of a particular type. In the unbroken phase, at very high temperatures, the symmetry is intact. The four carriers of the unified force, the three W bosons and one B boson, are all massless. The force is unified. Electromagnetism and the weak force are not separate things. When the universe cooled and the Higgs field took on its non-zero value, the symmetry was broken. The W and Z bosons acquired mass from the Higgs mechanism. The photon remained massless. The unified force separated into two apparently different forces with completely different ranges and strengths. What looks like two separate forces at low energies is actually one force viewed after symmetry breaking. This is a profound statement about the structure of reality. The diversity of forces we observe at low energies, at the energies of everyday experience, is not fundamental. It is a consequence of the specific phase the universe is in. At high energies, above the electroweak scale, the symmetry would be restored and the two forces would merge back into one. The Large Hadron Collider reaches energies high enough to see the heavy W and Z bosons, but not high enough to fully restore the electroweak symmetry. Future colliders operating at much higher energies might probe the true unified regime more directly. And beyond the electroweak unification, physicists have long hoped to unify all three non-gravitational forces, electromagnetism, the weak force, and the strong force, into a single grand unified force. Grand unified theories predict that at energies roughly 10 million billion times higher than the electroweak scale, all three forces merge into one. This is an energy far beyond any conceivable accelerator. But grand unified theories make testable predictions even at low energies. Most notably, grand unified theories predict that the proton is not stable, that the proton should eventually decay, with a lifetime that depends on the specific model. The simplest grand unified theories predicted proton decay with a lifetime of about 10 to the power of 30 years. This was tested by building large underground detectors and watching for proton decay. It was not found. The simplest grand unified theories were ruled out. More sophisticated models predict longer proton lifetimes, still within the reach of future large detectors. The search for proton decay is therefore a search for grand unification. And grand unification is the idea that the weak force, electromagnetism, and the strong force are all aspects of a single underlying force. The weak force is central to this story because its unification with electromagnetism has already been demonstrated. It is the template for the larger unification. There is also the question of gravity. Can gravity be incorporated into this unified picture? Can all four forces be unified into a single framework? This is the holy grail of theoretical physics, the theory of everything. String theory is the most developed candidate for such a theory. Loop quantum gravity is another approach, but no complete, experimentally confirmed theory of everything exists. The weak force, by being the force that was first unified with another force, the first step on the road toward a possible unified description of all of nature, occupies a special place in this grand theoretical project. Let us now think about something much more concrete and much closer to human experience. The role of the weak force in nuclear medicine and in everyday technology. The most direct daily encounter most people have with the weak force is in medical imaging. Positron emission tomography, known as PET scanning, uses radioactive isotopes that decay by emitting positrons. The positron is the antiparticle of the electron. When a radioactive nucleus undergoes beta plus decay, a proton in the nucleus is converted into a neutron by the weak force, emitting a positron and a neutrino. The positron travels a short distance in tissue, finds an electron, and the two annihilate, producing two gamma rays traveling in opposite directions. PET scanners detect these gamma ray pairs. By recording which pairs arrive simultaneously at opposite sides of the detector, the scanner can reconstruct where in the body the annihilation happened, and therefore where the radioactive isotope has accumulated. Different isotopes accumulate in different tissues and can reveal different physiological processes. Fluorine, 18 attached to glucose, accumulates in metabolically active tissues, revealing brain activity and cancer metabolism. Other isotopes reveal blood flow in the heart. Every PET scan is a direct application of the weak force. The transformation of a proton into a neutron, the emission of a positron, the subsequent annihilation and gamma ray production, all of it traces back to the weak interaction. The images that doctors use to diagnose cancer, to measure brain activity, to assess heart function, are images made possible by the weak force. Radiocarbon dating, the technique that allows archaeologists and historians to determine the age of organic materials up to about 50,000 years old, also relies on the weak force. Carbon-14, a radioactive isotope of carbon, is produced in the atmosphere by cosmic ray interactions and is incorporated into living organisms as they take in carbon dioxide. When an organism dies, it stops incorporating new carbon. The carbon-14 it contains then decays, with a half-life of about 5,700 years by beta decay, the weak force converting a neutron into a proton and emitting an electron and an antineutrino. By measuring the ratio of carbon-14 to stable carbon-12 in an organic sample, chemists can calculate how long it has been since the organism died. The technique has revolutionized archaeology and our understanding of human prehistory. Every date from radiocarbon dating, every age determination of an ancient artifact, every confirmation of a historical timeline is made possible by the weak force. The force that makes neutrons decay, the force that operates at distances smaller than 1,000th of a proton diameter. Nuclear power plants also depend critically on the weak force. The chain reactions in nuclear reactors involve uranium or plutonium nuclei fissioning, splitting apart into smaller nuclei. The fission fragments are typically neutron-rich, having more neutrons relative to protons than the stable isotopes of their elements. These neutron-rich fragments undergo beta decay, the weak force converting neutrons into protons to reach stable configurations. The energy released in these beta decays contributes to the heat output of the reactor. The timing of the decays, the half-lives of various fission products, is crucial to reactor control. The weak force is woven into every aspect of nuclear reactor physics. And in nuclear weapons, the same physics applies. The energy release in a fission weapon comes partly from the fission itself and partly from the rapid decay of fission products. The weak force sets the timescale of those decays. It determines which fission products are short-lived and which persist as long-term radioactive contamination. The pattern of radioactive fallout, the specific isotopes that are dangerous and for how long, is entirely determined by the properties of weak force decays. The weak force is not peripheral to human technology. It is embedded in our most advanced medical instruments, our most precise dating techniques, our most powerful energy sources, and our most destructive weapons. The force that operates at distances smaller than any we can directly perceive has effects that reach across the scales of human history and human civilization. Now let us return to something fundamental that we have not yet fully explored: the specific structure of the weak force and why it is left-handed in a deep sense. The Standard Model describes the weak force as a gauge theory based on a symmetry group called SU2. This is a mathematical group that describes rotations in a two-dimensional complex space. The weak force mixes together pairs of particles, the up quark and the down quark, the electron and the electron neutrino, the muon and the muon neutrino, the tau and the tau neutrino. Each pair is called a weak isospin doublet. The key point is that only the left-handed components of these particles are paired into doublets. The right-handed components of quarks and charged leptons are SU2 singlets, meaning the weak force does not mix them. The right-handed neutrino is not in the theory at all in the original Standard Model. This asymmetric treatment of left-handed and right-handed particles is the mathematical root of parity violation. When the W boson is exchanged between particles, it only couples to left-handed particles. The right-handed components simply do not feel it. This is not a consequence of anything deeper in the Standard Model. It is an assumption built into the theory's structure from the beginning. Why is the weak force left-handed? We do not know. The Standard Model tells us that it is, and the Standard Model's predictions match every experiment we have done. But the Standard Model does not explain why it is left-handed rather than right-handed or symmetric between the two. It is a fundamental, unexplained feature of the theory. Some physicists find this deeply unsatisfying. A fundamental force of nature having an inherent preference for left-handedness, with no explanation for why left rather than right, seems arbitrary. It suggests that either there is a deeper theory that explains this preference, or that the left-handedness arose from some symmetry-breaking process in the early universe that we do not yet understand. Left-right symmetric extensions of the Standard Model propose that at very high energies, there is a mirrored W boson, a right-handed W boson called WR, that couples to right-handed particles. At high energies, the theory is fully symmetric between left and right. But WR is very heavy, much heavier than the ordinary W boson, and at low energies the WR is too heavy to be relevant. The apparent left-handedness of the weak force at low energies is a consequence of the much higher mass of the right-handed W boson, not a fundamental asymmetry of the laws of physics. These left-right symmetric models also naturally explain neutrino mass through the seesaw mechanism. If right-handed neutrinos exist and are very heavy, the light neutrinos we observe acquire small masses through a mathematical seesaw. The heavier the right-handed neutrino, the lighter the ordinary left-handed neutrino. This naturally explains why neutrinos are so much lighter than all other massive particles. And the same right-handed neutrinos that give mass to ordinary neutrinos can, through their decays in the early universe, generate the CP violation and lepton asymmetry that leads to the matter-antimatter asymmetry we observe today. The current and future programs of particle physics experiments include searches for right-handed W bosons and right-handed neutrinos. Finding them would transform our understanding of the weak force. It would show that the apparent left-handedness of the weak force is not fundamental but emergent, a low-energy consequence of a more symmetric underlying theory. And it would connect the structure of the weak force directly to the explanation of why the universe contains matter. These experiments are running now. The Large Hadron Collider is searching for right-handed W bosons. Neutrino experiments are searching for signatures of the heavy right-handed neutrinos through a process called neutrinoless double beta decay. If a neutrino is its own antiparticle, a Majorana fermion, then the process where a nucleus undergoes two simultaneous beta decays with no neutrinos emitted becomes possible. This process violates lepton number conservation, which is characteristic of the Majorana nature of the neutrino and of the seesaw mechanism. Finding neutrinoless double beta decay would confirm both the Majorana nature of the neutrino and, indirectly, the existence of the heavy right-handed neutrinos whose decays may have generated all the matter in the universe. The search for neutrinoless double beta decay is one of the most important experimental programs in fundamental physics. Experiments like CUOR in Italy, CamLandZen in Japan, and EXO 200 in the United States are searching for this rare process with increasing sensitivity. So far, it has not been found. The limits on its rate have been pushed lower and lower, constraining the mass of the Majorana neutrino. Future experiments will go further still. If it is found, the implications will be enormous. It will confirm the Majorana nature of the neutrino. It will confirm lepton number violation. It will strongly support the seesaw mechanism and the existence of heavy right-handed neutrinos. And it will point directly toward leptogenesis as the explanation for the matter-antimatter asymmetry. The reason the universe contains matter may be found in a decay process occurring at a rate of less than 1 event per year per 100 kilograms of material, in detectors buried deep underground to shield them from cosmic rays. Physics finds big answers in the smallest signals. The weak force, operating at distances smaller than 1,000th of a proton, producing effects so rare that they occur less than once per year in 100 kilograms of carefully chosen material, may hold the answer to why the universe exists. That is the weak force. The most overlooked, the most underestimated, the most philosophically consequential force in nature. It transforms particles. It breaks symmetry. It powers the sun. It makes the elements. It kills neutrons. It produces neutrinos by the trillion. It treats left and right differently in a way that the universe does not. And it may have written the difference between a universe full of matter and a universe of pure radiation into the fabric of physics itself, in a tiny CP-violating phase in a matrix of numbers, in the first fraction of a second after the Big Bang. Right now, 100 trillion neutrinos are passing through your body, products of the weak force, produced in the solar core, carrying information about reactions that happen at the center of a star, passing through you without leaving a trace, continuing into the cosmos, carrying their quiet message about the force that makes the sun shine, the force that nobody talks about, the force that makes everything possible, the weak nuclear force, working, always, in the place too small to see, at the scale too brief to measure, doing the most essential things in the universe, without recognition, without pause, and without ever stopping. Let us go deeper into something that connects the weak force to one of the most dramatic moments in the history of experimental physics. The moment when a single experiment overturned one of the most deeply held assumptions about the nature of reality. Because understanding what Wu's experiment actually measured and why it was so shocking requires understanding what physicists believed about symmetry before 1957. Before 1957, symmetry was not just a useful concept in physics. It was almost a philosophical conviction. The idea that the laws of nature treat left and right the same, that the universe has no preferred handedness, seemed self-evidently correct. Why would the universe care about left and right? What would even define left and right at the fundamental level if the laws of physics treated them identically? This was not idle philosophy. It was built into theoretical physics at a deep level. Parity symmetry, the symmetry under mirror reflection, was assumed to be exact. It was used in calculations. It constrained what interactions were possible. Violations of parity would have been not just surprising, but philosophically troubling, suggesting that the universe had an inherent handedness with no apparent reason or origin. The assumption was so deeply embedded that when Li and Yang reviewed the evidence and found it lacking, most physicists reacted not by reconsidering the assumption, but by questioning the review. Surely parity had been tested. Surely this was known. But when Li and Yang looked carefully, the tests had all been done in strong force or electromagnetic interactions. The weak interaction had never been carefully tested. The assumption had simply been carried over without experimental foundation. Chien-Shiung Wu was one of the most skilled experimentalists of her generation. She had spent years studying beta decay and knew the technical challenges of the field intimately. She designed the experiment carefully, cooling cobalt-60 to temperatures near absolute zero to prevent thermal fluctuations from randomizing the nuclear spins, aligning the spins with a strong magnetic field, and measuring the angular distribution of the emitted electrons using sensitive detectors. The alignment of the nuclear spins gave the system a definite handedness. If you look at a spinning cobalt-60 nucleus from the north pole of the magnetic field, the spin is counterclockwise. That counterclockwise spin defines a left-handed orientation. The question was, do more electrons come out from the north pole, the left-handed direction, or from the South Pole, the right-handed direction? If parity were conserved, the answer would be equal. The process and its mirror image would be identical. Equal numbers of electrons north and south. They were not equal. Far more electrons came out from the South Pole, the direction opposite to the nuclear spin. The weak force, in emitting those electrons, strongly preferred one direction over the other. The mirror image of the process would have more electrons going north. But the mirror image process simply did not happen as often as the mirror predicted. Parity was violated. Maximally violated. The weak force was not just slightly asymmetric between left and right. It was completely asymmetric. The W boson, when it was emitted, preferred with maximum possible strength to couple to left-handed particles. The violation was not a small correction. It was the entire effect. When Wu called colleagues at Columbia to share the results, the news spread through physics immediately. Pauli wrote his famous letter expressing shock. Feynman made his bet and lost. The assumption that had been so natural, so philosophically comfortable, so built into the theoretical framework, was simply wrong. The universe at its most fundamental level was not symmetric between left and right. And physics had to absorb this, had to rebuild its intuitions, had to accept that the weak force, the force responsible for beta decay and for the transformation of particles, was fundamentally asymmetric between the two handednesses that classical intuition treated as equivalent. This acceptance changed physics permanently. Once parity violation was established in the weak interaction, physicists could no longer assume that any symmetry was exact just because it seemed philosophically natural. Every assumed symmetry had to be tested, and the tests revealed further surprises. CP violation, discovered by Cronin and Fitch in 1964, was another blow to symmetry assumptions. Even the combined symmetry of parity and charge conjugation, which had seemed like a safe refuge after parity alone was violated, turned out to be broken by the weak force. The universe not only treats left and right differently, it treats matter and antimatter differently in their mirror images. The violation is small, but it is real and it is measured, and the search continues. T violation, the violation of time reversal symmetry, has also been found in weak interactions involving kaons and beam mesons. The CPT theorem, one of the most fundamental results of quantum field theory, states that the combined symmetry of charge conjugation, parity, and time reversal must be preserved in any Lorentz invariant local quantum field theory. Since CP is violated, T must also be violated by exactly the right amount to preserve CPT, and measurements confirm this. So the weak force violates P, violates C, violates CP, violates T. It preserves only the combined CPT symmetry, which it must preserve if the standard model is consistent. The weak force is the great symmetry breaker of the standard model, the force that challenged and overturned the most natural and comfortable assumptions about the structure of physical law. And each violation it imposed on physics turned out to be not just a curiosity, but a deep clue about the nature of reality. The CP violation is likely connected to the matter-antimatter asymmetry of the universe. The parity violation shapes the structure of the neutrino, the fact that neutrinos are always left-handed, which is connected to why neutrinos are so light through the seesaw mechanism, which is connected to leptogenesis, which is connected to why there is matter in the universe. The weak force breaks symmetries, and every broken symmetry tells you something profound about where the universe came from and why it is the way it is. Now let us think about the three generations of matter and what the weak force tells us about them. The standard model contains three generations of quarks and leptons. The first generation, up quark, down quark, electron, electron neutrino. The second generation, charm quark, strange quark, muon, muon neutrino. The third generation, top quark, bottom quark, tau, tau neutrino. Each generation is like a heavier copy of the first. The second generation particles have the same charges and the same weak force interactions as the first generation particles, but are much heavier. The third generation particles are heavier still. Why are there three generations? Nobody knows. The standard model accommodates three generations, but does not explain why there are three rather than 1 or 4 or 12. It is one of the great unexplained facts of particle physics. But the weak force tells us something important about the generations. It mixes them. The W boson does not just convert an up quark into a down quark. It can convert an up quark into a strange quark or a bottom quark, quarks from the second and third generations. These transitions are suppressed relative to the within-generation transitions, but they are not forbidden. The mixing between generations is described by the CKM matrix, and the mixing between lepton generations is described by the PMNS matrix for neutrinos. The existence of 3 generations and the specific mixing angles between them are what makes CP violation possible. 2 generations are not enough. With only 2 generations of quarks, the CKM matrix is real and contains no complex phase, meaning no CP violation. 3 generations are the minimum necessary for CP violation to occur through this mechanism. The fact that there are exactly 3 generations may not be a coincidence. It may be the minimum number needed for a universe that can generate the matter-antimatter asymmetry through weak force CP violation. Whether nature is that economical, whether there are exactly 3 generations because fewer would not allow matter to dominate, is speculative. But it is a remarkable coincidence, if it is a coincidence, that the minimum number of generations needed for this mechanism is exactly what is observed. The weak force, by mixing generations and generating CP violation, constrains what the structure of matter must look like for a matter-dominated universe to exist. The 3 generations are connected to the CP violation, which is connected to the matter-antimatter asymmetry, which is connected to our existence. The number of particle generations may be not an arbitrary fact, but a necessary one. Let us also briefly consider what the Standard Model does not explain about the weak force, to be honest about the boundaries of our knowledge. The Standard Model successfully describes all known weak force phenomena. The decay rates of every particle that decays via the weak force match the predictions. The properties of the W and Z bosons match the predictions. The patterns of quark and neutrino mixing match the structure of the CKM and PMNS matrices. CP violation has been measured and matches the theoretical framework. But the Standard Model does not explain the masses of the W and Z bosons from first principles. It uses the Higgs mechanism to give them mass, but the specific mass values depend on parameters of the Higgs field, which are not explained by the theory, but simply measured and plugged in. Why the W boson has the mass it has, 80 gigaelectronvolts rather than some other value, is not explained. It is a parameter. The Standard Model does not explain why there are 3 generations. It does not explain why the weak force mixes quark generations with the specific mixing angles encoded in the CKM matrix. It does not explain why parity is violated maximally, why the weak force couples only to left-handed particles rather than to both-handednesses. It accommodates all of these facts, but does not derive them from anything deeper. And the Standard Model does not explain where the matter-antimatter asymmetry of the universe comes from. The CP violation within the Standard Model is too small by many orders of magnitude. Something additional is needed. What that something is remains unknown. These gaps in our understanding of the weak force are among the most important open questions in physics. They are the places where new physics is most likely to be found. The experiments searching for neutrinoless double beta decay, for right-handed W bosons, for heavy neutrinos, for additional sources of CP violation, all motivated by the gaps in the Standard Model's description of the weak force. The weak force is understood well enough to make predictions that match every experiment we have done. And yet at its deepest level, its most fundamental structure, why it is the way it is, remains mysterious. This is the situation in physics. The known is extensive. The confirmed is impressive. The understood is genuinely deep. And the unknown is deeper still. The weak force sits at the center of that unknown, the most symmetry-breaking force, the only particle-transforming force, the force connected to the origin of matter and to the deepest unanswered questions about why the universe is what it is. Tonight you know it. You know what it does and why it matters. You know about Wu's experiment and the shock of 1957. You know about the neutrino and its ghostly passage through everything. You know about CP violation and its connection to matter survival. And you know that the deepest answers, the reason there is matter in the universe rather than nothing, the explanation for the 3 generations, the origin of the left-handedness of the force, are still waiting, still out there, encoded somewhere in the data that experiments are collecting right now. in the patterns of decays and oscillations and asymmetries that future physics will have to explain. The weak force is not finished with physics, and physics is not finished with the weak force. The most overlooked force in the universe still has its deepest secret to reveal. Right now, in a laboratory somewhere, a cobalt nucleus is decaying. A down quark is emitting a virtual W- boson. The W- lasts for less than a trillionth of a second before decaying into an electron and an antineutrino. The electron goes south. The antineutrino goes everywhere and nowhere, passing through the Earth and out the other side in the time it takes light to cross an atom. And the universe, in that moment, treats left and right differently, treats matter and antimatter differently, does something that no other force does, in a way that no mirror image could replicate, in the smallest space and shortest time that physics has ever probed. The weak force, working in the dark, holding the answer to why anything exists, still keeping its deepest secret. For now, there is one more thing worth sitting with before tonight is over. Something about the relationship between the weak force and time itself. The weak force violates time reversal symmetry, not on its own, but as a consequence of violating CP symmetry. The CPT theorem, one of the pillars of quantum field theory, requires that if CP is violated, then T must also be violated, so that the combined CPT symmetry is preserved. This is not just a mathematical requirement. It has physical meaning. Time reversal symmetry means that if you filmed a physical process and played the film backward, the reverse process would also be physically valid, would also obey the laws of physics. For most physical processes, this is true. A ball bouncing under gravity, played backward, shows a ball bouncing under gravity. A collision between billiard balls, played backward, shows a collision between billiard balls. Classical physics is time reversal symmetric. Quantum mechanics is mostly time reversal symmetric too. A quantum state evolving forward in time under the Schrödinger equation, played backward, gives another valid quantum evolution. Most quantum processes could equally well run in either direction, but certain weak force processes cannot. The decays of kaons and B mesons, when played backward, give processes that are not what actually happens. The time reverse process would happen at a different rate. The universe is not symmetric between past and future at the level of weak force processes. This has a deep connection to one of the most profound mysteries in physics, the arrow of time, the fact that time flows in one direction, that the past is different from the future, that you remember yesterday but not tomorrow, that broken eggs do not reassemble, that entropy increases. The thermodynamic arrow of time, the direction of increasing entropy, is usually explained by statistical mechanics and the initial conditions of the universe, not by microscopic physical laws. The laws themselves are mostly time-symmetric, but the weak force T violation is a fundamental, dynamical source of time asymmetry in the laws themselves, not just in initial conditions. Whether the weak force T violation is connected to the thermodynamic arrow of time, whether it plays any role in why time flows in one direction for macroscopic systems, is not understood. The two phenomena, microscopic T violation and macroscopic time asymmetry, may be related or they may be independent. Physicists do not have a clear answer, but the weak force is the only force that builds a direction of time into its own dynamical rules. Every other force is time-symmetric at the microscopic level. Only the weak force, through its CP and therefore T violation, breaks the symmetry between past and future in the fundamental equations. The most overlooked force in the universe is also the most philosophically loaded. It breaks left-right symmetry. It breaks matter-antimatter symmetry. It breaks time reversal symmetry. It is the force that, more than any other, introduces asymmetry into the laws of physics. The force that makes the universe not a perfect, symmetric, featureless place, but a place with handedness, with a matter preference, with a direction of time. The weak force is what makes the universe asymmetric enough to be interesting, symmetric enough to be mathematically beautiful, but broken enough to contain matter, to contain structure, to contain complexity, to contain life. Without the symmetry breaking of the weak force, there would be nothing to see in any direction. No matter to form stars, no time arrow to give history a direction, no handedness to distinguish left from right, just a perfect, Featureless, empty symmetry. The weak force is what breaks that symmetry. What cracks open the perfect emptiness and lets something emerge. What puts the difference between before and after, between matter and antimatter, between left and right, into the laws of the universe. It does all of this at a distance smaller than 1,000th of a proton, in a time shorter than 1,000,000,000,000th of a second, through particles so heavy they required the most powerful accelerators ever built to create. Quietly, constantly, without fanfare, inside every nucleus that decays, inside the core of every star that burns, inside every neutrino that passes through your body and through the Earth and through everything that has ever existed. The weak force, the most overlooked thing in the universe, and perhaps the most important, because it is what made a universe with something in it, rather than nothing. What gave time a direction? What made you possible? Tonight, that is enough. There is a version of physics education that teaches you 4 forces and moves on. Gravity, electromagnetism, the strong force, the weak force. Here are their ranges. Here are their strengths. Here are their carrier particles. Now you know them all. Move on. That version skips everything important. The weak force is not just a force with properties to memorize. It is the force that violated every symmetry physicists thought was sacred. It is the force that produced one of the greatest experimental shocks in the history of science, when Wu's cobalt nuclei sent their electrons south and the assumption of mirror symmetry collapsed in the data. It is the force that opened questions about left and right and matter and antimatter and time that are still unanswered 60 years later. The weak force is where physics learned that its most natural assumptions could be wrong, that beauty and symmetry, while guides, are not guarantees, that the universe is under no obligation to be as symmetric as physicists would like, that nature can and does have preferences for handedness, for matter over antimatter, for one direction of time over another, that the laws of physics had to accommodate rather than exclude. This lesson, learned through the weak force, has shaped how particle physicists approach their field ever since 1957. They no longer assume symmetries are exact without testing them. They test every symmetry they can. They look for violations. They expect surprises. They have learned from the weak force that surprises come from exactly the places where the assumptions were most comfortable. And the weak force is still producing surprises. The hints of CP violation in neutrino oscillations from the T2K experiment are the most recent chapter. The ongoing searches for neutrinoless double beta decay are the next test. The future precision measurements of neutrino properties at upcoming experiments like DUNE and hyperchemiocandy will probe the weak force's behavior in the neutrino sector with unprecedented precision. The weak force still has things to teach physics. Things about CP violation, about neutrino mass, about the matter-antimatter asymmetry, about whether the right-handed W boson exists and what that would mean, about whether protons eventually decay through grand unified interactions and what that would tell us about the unification of forces. All of these are open questions. All of them require experiments that are either running now or planned for the coming decades. All of them circle around the weak force and its distinctive ability to break symmetries and transform particles. The most overlooked force in the universe is also the most scientifically active frontier, the place where the most important unanswered questions in particle physics are being addressed. And underneath all the experiments and all the theory and all the open questions is the simple, daily reality of the weak force doing what it has always done, making neutrons decay, transforming quarks, producing neutrinos, powering the sun, making isotopes that allow doctors to see inside human bodies and archaeologists to date ancient civilizations. Right now, inside a PET scanner in a hospital somewhere, a fluorine-18 nucleus is decaying by the weak force. A proton has become a neutron. A positron has been emitted. That positron has found an electron. 2 gamma rays are traveling in opposite directions through a patient's body. The scanner is detecting them. An image is forming. A doctor is looking at that image. And the weak force, the force responsible for every single step in that process, is operating silently, invisibly, in a space smaller than 1,000th of a proton diameter, for less time than any clock can measure. Saving a life. The most overlooked force in the universe. Saving a life. Right now. Without recognition. Without pause. in the smallest space and the briefest time that physics has ever found a force operating. That is the weak nuclear force. That is what it really is. And why? Without it, the universe would be dark and silent and empty. And you would not be here to ask why. Let us close tonight by thinking about what the weak force reveals about the practice of physics itself, about how knowledge advances, about what it means to hold an assumption and then have it overturned. Before 1956, parity conservation was not a hypothesis physicists were actively testing. It was an assumption so deeply embedded that it was used as a constraint rather than a claim. Physicists would say, the weak interaction must conserve parity, and use that to limit what decays were possible. They would reject theoretical proposals that violated parity without thinking carefully about whether they had evidence for parity conservation in weak interactions. This is a pattern that appears throughout the history of physics. An assumption becomes so natural, so philosophically attractive, so useful as a calculational tool, that it stops being questioned. It becomes load-bearing. Other things are built on top of it. And when it finally collapses, the collapse is felt all the way up through the structure that was built on it. Parity conservation was load-bearing in 1956. When Wu's experiment showed it was violated, the collapse was structural. Not just a surprise about one force. A rethinking of what symmetries could be assumed and what had to be tested. A rethinking of the relationship between theoretical elegance and experimental fact. This rethinking has served physics well ever since. The culture of particle physics, shaped partly by the shock of 1957, tends now toward empiricism over elegance. When a theoretical argument says a symmetry should be conserved, the response is to test it, not assume it. When experimental results challenge an assumption, the response is to take the data seriously, not to explain it away. The weak force produced this culture change. The most symmetry-violating force in nature, by violating symmetry so dramatically and so shockingly, taught physicists to be empiricists, to test their assumptions, to take surprises seriously, to let the universe tell them what is true rather than deciding in advance what the universe should be like. This is what the best science looks like. Holding assumptions lightly, being willing to be wrong, taking experimental results seriously even when they overturn comfortable beliefs, building theories that match evidence rather than evidence that confirms theories. The weak force modeled this for physics. It showed, in the starkest possible way, that the universe does not care what symmetries physicists consider natural. It has its own structure, its own preferences, its own symmetries and its own asymmetries. And discovering what those are requires looking, not assuming. Every particle physics experiment running today is following this lesson. Every search for parity violation in new contexts, every measurement of CP violation, every test of left-right symmetry at higher energies, every search for neutrinoless double beta decay is an experiment designed to test an assumption rather than confirm one, to ask the universe what is true rather than tell it what should be. This is the legacy of the weak force in the practice of physics. Not just the particles and forces it revealed, the epistemological lesson it taught, how to hold assumptions, how to take data seriously, how to let experiment lead theory rather than theory constrain experiment. And the weak force is still teaching. Its hints about CP violation in neutrino oscillations are being followed up with bigger, more precise experiments. Its apparent left-handedness is being tested at higher energies with searches for right-handed W bosons. Its connection to the matter-antimatter asymmetry is being probed through the search for neutrinoless double beta decay. The universe still has things to say through the weak force. And physics is still listening, still measuring, still taking the data seriously, still willing to be surprised. That willingness, that openness, that empiricism is itself a kind of legacy of the moment in 1957 when cold cobalt nuclei showed that the universe preferred one direction over another, and physics learned that its most natural assumptions about symmetry were not safe. The weak force broke our assumptions, and in breaking them, made physics better at finding the truth. That is the most important thing it ever did. More important than powering the sun. More important than making the elements. More important even than possibly explaining why matter survived the Big Bang. It made physicists humble. And humility, in science, is what makes discovery possible. The weak force. The most overlooked force. The most assumption-breaking force. The most philosophically consequential force. Operating right now, in the core of the sun, in every decaying nucleus, in every neutrino passing through your body, in every PET scanner, in every radiocarbon date, in every search for matter-antimatter asymmetry. Everywhere, quietly, doing the work that makes the universe possible, and reminding physics, every time it forgets, that the universe is always stranger and richer than any assumption. That is the weak nuclear force. That is what it really is. Good night. One final image to carry from tonight. Somewhere in the universe, far from here, a star is dying. A massive star, many times heavier than the sun, has exhausted its nuclear fuel. The iron core at its center has grown too heavy to support itself. Gravity wins. The core collapses in less than a second, a collapse so fast it defies comprehension, from a sphere the size of the Earth to a sphere roughly 20 kilometers across. The density reaches the density of nuclear matter. The collapse bounces. A shock wave forms and begins to move outward through the infalling stellar material. In the collapsed core, weak force interactions are happening at an extraordinary rate. Electrons are captured by protons, converting them to neutrons and emitting neutrinos. The temperature is so high that thermal neutrinos are produced in enormous numbers. In the first 10 seconds after the core collapse, the energy released by the weak force in the form of neutrinos exceeds the total energy output of the sun over its entire 10 billion year lifetime. The equivalent of about 3 times 10 to the power of 46 joules, released in 10 seconds, mostly as neutrinos. That neutrino pulse is what drives the supernova. The neutrinos deposit a fraction of their energy in the stellar material above the collapsing core, providing the energy that blows the outer layers of the star into space. The spectacular supernova explosion, visible across galaxies, is powered by the weak force, by neutrino interactions, by the same force that cannot reach beyond 1,000th of a proton diameter, depositing its energy with enough efficiency to blow a star apart. The elements heavier than iron, produced in the explosion by rapid neutron capture, the gold and the platinum and the uranium, are scattered into the interstellar medium by the explosion that the weak force drives. Those elements eventually find their way into new solar systems, into planets, into the chemistry of life. The gold in your jewelry was scattered into space by a neutrino-driven supernova explosion, by the weak force. You carry the weak force with you, in your gold jewelry, and in the iron in your blood, and in the carbon in your cells, and in the radioactive potassium in your bones that slowly decays by the weak force, and in the neutrinos that pass through you every second, and in the fact that the sun is shining today and will shine tomorrow. The weak force is everywhere in your life. You just cannot see it, because it operates in the smallest spaces for the briefest times, doing the most consequential things, without ever making itself directly apparent to any human sense. It is the hidden force, the overlooked force, the underestimated force, and tonight you know it is there. And knowing it is there changes how you see the sun, how you see your own body, how you see the gold and the iron and the carbon that you are made of, how you see the universe that is apparently full of matter rather than nothing. All of it connected, through chains of physics, to a force operating in a space smaller than anything you can see, for a time shorter than anything you can measure. The weak nuclear force, the most important thing you have never thought about, until tonight. And if that is not enough, consider this one final thought. The neutrinos streaming through your body right now were produced in the solar core 8 minutes ago. 8 minutes ago, deep inside a ball of plasma 150 million kilometers away, a proton emitted a virtual W boson. The W boson lasted for less than 10 to the power of negative 25 seconds. It decayed into a positron and a neutrino. The neutrino traveled outward through the sun in about 2 seconds. Then it crossed the distance between the sun and the Earth in about 8 minutes. And then it passed through you. In the time it took that neutrino to travel from the solar core to your body, nothing else in the chain of events that produced it lasted more than a trillionth of a second. The W boson that created it was born and died in a time so short that light could not travel across a single proton during its lifetime. From the trillionth of a second of the W boson to the 8 minutes of the neutrino's journey, the weak force connecting them, the force that operates at one scale, enabling a particle that crosses the solar system. That is the range of the weak force's consequences. From the incomprehensibly small to the astronomically large. From the briefest interaction to the journey that spans 150 million kilometers. And then through you, without leaving a trace. The weak force. In you. Right now. Always.